For this lesson, we are going to be talking about how to apply the equations of our conic section. So we're going to start off with circles. So for our first problem, we have, on average, the circular eye of a hurricane is about 15 miles in diameter, with gale winds that can affect an area up to 300 miles from the center of the storm. So the landfall of the eye of a hurricane can be represented by the point 3270 on the coordinate grid. So we need to write an equation to represent A, the area of the eye, and then B, the area affected by the winds. So first, we are going to look at that coordinate for landfall as our center. So for part A, we will have x minus 32 squared plus y minus 70 squared. And then we are going to need our radius. So this is for the eye. So we know that the eye is 15 miles in diameter. So half of that is 7.5. So we'll need 7.5 squared. Well, 7.5 squared is 56.25. So then for part B, we need to find the area affected by the winds. So since we have an area up to 300 miles away from the center, we can actually use 300 as our radius. So we're going to have the same center. And then we are going to need 300 squared, which is going to be 90,000 miles. And so that is our answer for part B. So for number 2 here, we are still using circles, and we have the beam of a lighthouse can be seen for up to 25 miles. A boat is located 20 miles west and 18 miles south of the lighthouse. So we need to write, first of all, an equality to represent the region lit by the lighthouse beam, and then B, determine whether the beam can be seen from the boat or not. So if we use the lighthouse as essentially 0, 0, so I'm going to kind of draw a graph here. And so our lighthouse is going to be 0, 0, then anywhere from 25 miles around it is going to be able to see the light. So that equation, we can do x squared plus y squared is less than or equal to, let's see, 25 squared is 625. So that takes care of A. Now for B, we are going to see if the boat can see the light of the lighthouse. So if we go 20 miles to the west, so that would be this direction, 20 miles, and then 18 miles to the south, we need to see if it's going to fit within that 25-mile radius. So what we can do is we can take that equation and see if it creates a true statement. So we'll have 20 squared, actually that'll be negative 20 squared, and then plus negative 18 squared is less than or equal to 625. So once we work this out, we have 400 plus 324, and that adds up to 724, and that is not less than 625. So no, the lighthouse's beam cannot be seen from this boat. So let's look now at ellipses and some applications that we can use for those. So we have a glass window in the shape of an ellipse, has a major axis of 60 inches. So that's going to be the longest axis. And an eccentricity of 0.7. So we need to write an equation to represent the outline of the window. So since we know our eccentricity, then we can use that to find our B, because we need both our major and minor axis. We're going to go ahead and call the center of our window 0, 0 though. So A is going to equal 30. And so then we're going to need to back up and find our C, which will then let us find our B. So if we know our eccentricity is C over A, we know that is 0.7, and our A should be 30. Then when we multiply, we should get 21 equals C, and then we can use C squared equals A squared minus B squared to find our B. So we have 21 squared equals 30 squared minus B squared. 21 squared is 441. 30 squared is 900 minus B squared. And then we need to subtract. So that gets us 459 equals B squared. And honestly, we could just stop there, because if we go any further, we don't really need to go further, because we need our B squared to write our equation. So since our center is 0, 0, we're not going to add or subtract anything to x or y. So we have x squared over 900 plus y squared over 459 equals 1. So then on number 4, we have an entrance to a tunnel is in the shape of a half ellipse and has a width of 40 feet and a height of 25 feet at its center. So we have a height of 25 and a width of 40. And so we need to find the height of the tunnel 15 feet from the center. So what we are actually looking for is, if we go over 15 feet, how tall are we there? So let's first write an equation for this ellipse. So since this is a half ellipse, then we are going to need to consider that 25 as our A, because 25 plus 25 would be 50. And so that would actually be our major axis. And then B should be 20. And so if we use that center as 0, 0 again, we can have x squared over 625. Actually, I think this is going to be a vertical. So let's go ahead and do x squared over 400 plus y squared over 625. And that's going to equal 1. So that is the equation that we're going to work with. So now we need our height at 15 feet from the center. So which side it's on doesn't really matter, but we are going to go ahead and put that in for x. So we're going to have 15 squared over 400 plus y squared over 625 equals 1. And then 15 squared is 225 over 400 And now we are going to go ahead and subtract that 225 over 400. And we can actually reduce it if we want to, because it reduces to 9 over 16. But when we subtract that 9 over 16, that is going to give us y squared over 625 equals 7 over 16. And then we can multiply by 625 to get that y squared alone. So 7 over 16 times 625 gives us, not a perfect fraction, but that gives us 4375 over 16. And when we take the square root, that gives us y equals, and this is going to be plus since we are dealing with a length. And so we're going to have the square root of 4375 over 4, or that is a decimal, that is approximately 16.54 feet. Okay, so let's look at another one for ellipses. So we have that the planets travel in an elliptical orbit with the sun at its focus. So Mercury is 43.4 million miles away from the sun, and the sun at its furthest point, and 28.5 million miles at its closest point. So we need to find A, the eccentricity of the orbit, and then B, an equation to represent its path. So we are going to look at, see, so we have this ellipse. Actually, I'm going to make it a little bit wider. And so the sun is one of the foci, so it's not the center. And so we are at the closest point, the sun is 28.5 million miles from Mercury. And then at the furthest point, it is 43.4 million miles. So we are going to add these two values together to make up the length of our major axis. So that's going to be 2a is 43.4 plus 28.5. And so then 2a is 71.9, and then divide by 2. So A equals 35.95. And so then we can find our eccentricity by first finding our C. So C is going to be the distance from the center to the foci. So we essentially are finding what that distance is here. And so C is going to be 35.95 minus that 28.5. So that is going to be 7.45. So then to find our eccentricity, which is part A, we have E equals C over A. And so E is going to equal C, which is 7.45 over A, which is 35.95. And so that gives us approximately 0.21. And then to write this equation, we are going to need our B value. So we are going to use C squared equals A squared minus B squared. So C squared is going to be that 7.45 squared equals 35.95 squared minus B squared. So we have 7.45 squared, and that gives us 55.525 equals 35.95 squared. And that is 1292.4025 minus B squared. So we are going to subtract those values. And that gives us a, 1236.9 equals B squared. So we're going to take the square root. And so we have approximately 35.17 as our B, but we actually could back up and just use that 1236.9 as our B. So now we can go ahead and write our equation. So we're going to have x squared over our A, which is 35.95 squared. And that gives us 1292.4025 plus our y squared over 1236.9 equals 1. So let's look at our hyperbolas now. So on number 6, we have a nuclear cooling tower is hyperboloid, essentially a hyperbola rotated around its conjugate axis. So you can almost see like your hyperbola here on the edges of the tower. And the tower has a diameter of 64 feet at its narrowest point and a distance of 116 feet in between foci. So our foci have 116 feet. So our A is essentially going to be 32. Actually, our foci would not go that way. So 116 feet in between foci. So half of 116 is going to be 58. And so C is 58. A is 32. And so we can actually use our Pythagorean theorem, C squared equals A squared plus B squared, to find what B is, because we will have 58 squared equals 32 squared plus B squared. So we have 58 squared as 3,364. And then 32 squared is 1,024. And so 3364 minus 1024, that gives us 2340 as b squared. And I'm actually not going to go any further than that because we're writing the equation for this, so we actually need that b squared value. So we are going to have x squared over, and then our a squared was actually 1024 minus y squared, which is b squared, which is 2340 equals 1. So on number 7, we have two ships located exactly 2 miles apart hear an explosion. Ship B hears the explosion 8 seconds after ship A hears it. If the difference in times that the ships hear the explosion is constant on a hyperbola with the two ships at the foci, find the equation of the horizontal hyperbola on which the explosion is located. Note, sound travels at 1100 feet per second. So we are given the clue that we are on a horizontal hyperbola. So we are going to have x squared over a squared minus y squared over b squared equals 1. So for our a, that comes from ship A being on the foci and ship B hearing the explosion 8 seconds after ship A. So if sound travels at 1100 feet per second, then we have 8 times 1100. That will give us our length of A, and then we'll need to divide it by 2. So that is 4,400 feet. Now, since we know that the ships are 2 miles apart and they are located on the foci, then we know that C has to be 5,280 because that's a mile in feet. So this does give us enough information to find B because we can use Pythagorean theorem. So we will have 5,280 squared equals 400 or 4,400 squared plus b squared. And so that 5,280 squared minus, and so that gives us 8,518,400 for b squared. And since we are writing the equation, that is where we are going to leave that value because there's no point in taking the square root. So we're going to have x squared over, and then the 4,400 squared is, see, 19,360,000 minus y squared over 8,518,400, and it equals 1. Right, so last we have parabolas. So in our first question, we have a surveyor found a circular pond with a 36-foot diameter that has a cross-section in the shape of a parabola. So if the middle of the pond is 12 feet deep, how deep is the pond? 8 feet from the edge. So we have a pond, and since it has the shape of a parabola, then we are going to go ahead and just use that. So we're going to go ahead and call our focus here 0, 0. And so then at the deepest part, that is going to be a 0, -12, and that's going to be our vertex. So our axis of symmetry is actually here at 0 as well. And so our pond is 36 feet in diameter. And so that is going to be, let's see, 18 on each side. And so we could go ahead and write this. See, we are pretty close to there. So actually what we don't know is that if we have the latus rectum of the pond or not. So what we're going to do is we are going to go ahead and plug in 18 as our coordinate and 0. And because we do have enough information to go ahead and back up and find P. So we have so far x squared equals 4p and then y plus 12. Because we know that our vertex is 0, 12. And so we're going to go ahead and plug in 18 and 0. So we have 18 squared equals 4p and then 0 plus 12. So 18 squared is 324, and that is going to equal 48p. So if we divide by 48, then that leaves us with p equals 6.75. So actually our latus rectum is actually at 6.75 and 6.75. So the 18-0 could actually not be. And actually 0-0 then would not be our focus in that case. So we have the ability to write our equation now as x squared equals 4 times 6.75 times y plus 12. And so 4 times 6.75 is 27, and that gives us y plus 12. So we have x squared equals 27 times y plus 12. And then we can go ahead and plug in where we are for 8 feet from the edge. So 8 feet from the edge is actually 10 feet from the center of the pond. So we're going to use 10 as our x. So we have 10 squared equals 27y. And then 27 times 12 is 324. So we have 100 equals 27y plus 324. And then we are going to subtract. So we have a negative 224 equals 27y. And then negative 224 divided by 27 is approximately a negative 8.3. And so the pond is 8.3 feet deep, 8 feet from the edge. So for number 9, we have a cable connecting the towers of a bridge is suspended in the shape of a parabola. The towers are 1,200 meters apart and stand 120 meters above the roadway. If the cable touches the road at the midpoint of the towers, write an equation for the parabolic shape of the cable. Okay, so if we go ahead and call, let's see, the distance between the tops of the two towers, and we're going to go ahead and say that that's 600 on this side and 600 on this side. Here's our two towers. And then that parabolic shape is between them. So that's going to be 0, 120, actually negative 120 for that point. And so we will have, see, we'll just have to solve for p again. So we will have x squared equals 4p times y plus 120. And so we'll put in our point of 600, 0. So we will have 600 squared equals 4p times 0 plus 120. And so 600 squared is 360,000. And that equals, let's see, that's going to be 480p. So we're going to divide by 480. And that gives us 750p. So then we can go ahead and write our equation. So we will have x squared equals 4 times 750 times y plus 120. And then 4 times 750 is 3,000. And so there is our equation. Okay, so for our last question, we have a satellite dish with a parabolic cross section is 20 feet wide at its opening. So we have a picture here, but I'm going to go ahead and kind of draw that dish shape. So it's 20 feet wide. And if the focus is 6 feet from the vertex, so we're just going to go ahead and call this point the focus. So we have 6 feet. We need to write an equation of the parabolic cross section using the vertex as the origin. So this is going to be 0, 0. So we are going to, and then we're going to need to find the depth of the satellite at the vertex. So this is kind of a vertical satellite. So we are going to use, let's see, y squared equals, and then 4 times 6 is 24 times x, because of course x1 is 0 since we're using the origin as the vertex. And then since it is 20 feet across, that is 10 feet on each side. So we can go ahead and put in a 10 for our y. So 10 squared equals 24x. That is 100 equals 24x. And then divide by 24. And so that gives us, let's see, 25 over 6, which is really 4.16 repeating. So approximately 4.17 feet for our depth.